All right, so we're going to get started with what looks like a repeat of the last video, but I assure you we're working on a different equation. If you look, we have another quadratic that's in factored form. This time I actually have a number out front. Last time I only had two parenthetical statements. This time I have a number out front, and we're going to see how that affects what the graph looks like, what the equation looks like, and all the rest. So just again, in case it's a little bit strange thinking of this as a quadratic, let's work on foiling out these two pieces. So first I say x times x and x times -1, and then 4 times x and 4 times -1. We'll keep the rest the same. So x times x gives me x squared. X times -1 gives me -x. 4 times x is 4x. And 4 times -1 is -4. Again, I have two like terms in the middle that I can combine. -x and positive 4x would give me positive 3x. And we're almost there. Now that we have this foiled out, we have this number -2 out front. So why don't we call that a coefficient. It's out front of the parentheses. And let's distribute that into our parentheses. -2 times x squared would be -2x squared. -2 times 3x would be -6x. And -2 times -4 would be +8. So again, this is what we call the standard form. It's not particularly useful for graphing, but it's very recognizable as a quadratic equation or quadratic function, because we see that the highest power here is a squared, x squared. We do have an x term, but we determine quadratic by what we call the leading term, the one with the highest power. And in this case, it's a squared term. It's a power of 2. And so we know that it is a quadratic. So that was just to show you a little bit of what this equation looks like, or this function looks like when we FOIL it out. We're not going to use it. It's not a required step, just so that in case you're wondering, like, is that an important step for us being able to graph this equation? And no, it's not. I'm just doing it for you so that you can see the connection between the factored form and the standard form. But let's go back to the factored form. Here it is. Whoops. I went off the screen there. Went a little crazy. There we go. Okay. Just like in the last example, I said factored forms are, or the factored form of a quadratic is useful in finding 3 pieces of information. 4 points, but 3 pieces of information. The first important piece of information is what we call the zeros, or the x-intercepts. That's where they intersect the x-axis. The second important piece of information that we can find is we can figure out where the axis of symmetry is, which also allows us to figure out where the vertex is. Now, I kind of brushed over that very quickly in the last video because I just wanted you to kind of get the overview. But we'll talk about that a little bit more specifically in this example. And then lastly, we're also able to figure out the y-intercept if we are interested to find that. So let's see if we can do that. I'm going to write this down here again. It's getting too cluttered up there. So -2 times x plus 4 times x minus 1. Let's think first about finding those zeros. And remember that in order to find where the function equals 0, where the whole function hits that horizon line, or where y equals 0, we have to make y 0. We have to figure out what does x have to be in order to get the whole equation to equal 0. And there are 2 ways to get that to happen, because we can either get this first piece to equal 0, and that will make the whole function 0, or we can get the second piece to equal 0, and that will again make the whole function 0 because of our 0 product rule. The first way to make it 0 is to get x plus 4 to equal 0. And we know that we could do that. If x was -4, if I were to plug in -4 here, it wouldn't matter what everything else in the equation was. If -4 plus 4 equaled 0, the whole thing would turn 0. So if x equals -4, we get a 0. Secondly, we could try to make the second piece 0. What would x need to be to get the second piece to equal 0? Well, it could equal just +1. If I plug in +1 here, 1 minus 1 will be 0. It doesn't matter what the rest of the equation is. If that one part is 0, when we multiply, the whole equation goes to 0. What does that look like on the graph? Well, those points, x equals -4 and x equals 1, are the points where we get x-intercepts. It's where the whole function goes to 0. Meaning where it has a y value of 0. So that's at x equals -4, 1, 2, 3, 4. And where x equals 1, right here. So we have found the first important piece of information. The second valuable piece of information that we can find is the y-intercept. Now, I'm skipping over the second, actually. I know I put axis of symmetry and vertex first, but in this particular case, the y-intercept is easier to find, so I'm going to do that next. The y-intercept, remember, we can always find by just making x 0. And that's because we hit the y-axis whenever the x value is 0. So we can plug in x equals 0, and it will tell us how high or how low to make this graph. So let's take our function, y equals -2 times x plus 4 times x minus 1. Let's find out what the y-intercept is by making x 0. So -2 times 0 plus 4, that's just 4, and 0 minus 1, it's just -1. So we get -2 times 4 times -1, which will give us a value of +8. -2 times 4 would be -8, but times -1 will be +8. So 1, 2, 3, 4, 5, 6, 7, 8. When we plug in 0 for x, we find out what the y-intercept is. So we now have, actually made that a little bit too big there. That works. I now have 3 valuable points for my graph. I still want to find at least one more, but we're starting to get an idea that this looks like an upside-down parabola, doesn't it? It looks like it's going to kind of swing up and go down. That's a very wobbly parabola. Don't worry, I'll erase that. But let's ask ourselves, does that make sense that this would be an upside-down parabola? In order to be an upside-down parabola, the coefficient in front of the x squared has to be negative. Let's look at our standard form over here. Here's x squared. Is the number out front negative? Yes, it is. So that shouldn't be too surprising. The negative number is causing us to have an upside-down U-shaped parabola. And so that's actually an interesting thing that we've now figured out by having these 3 points plotted. But we're not done yet. We also want to talk about the axis of symmetry. Now I said that very quickly. Actually, I think that's supposed to have 2 M's. We'll just ignore that for a minute. Drawing on a computer screen is just as difficult as drawing on a whiteboard, apparently. But an axis of symmetry means it's the line that shows where the mirror image of our parabola is. So if you think about a parabola, we'll do a right side up one first, always has this kind of line down the middle that shows that the left and the right side are exact mirror images of each other. And that line we call the axis of symmetry. Since we have 2 points here, we know that the axis of symmetry, just because of the nature of a mirror image, is going to have to be exactly in the middle of them. So since these are 1, 2, 3, 4, 5 units apart, they're going to be like, the middle would be like 2.5 units in. So right about right here, this would be the middle. So that's actually at -1.5. That line is going to divide our parabola in half. And the reason that that's helpful is that we know the vertex of the parabola, that bottom point, kind of what we call the corner of the parabola. Not that it's a corner, but the vertex is the technical name. That point is right there on the axis of symmetry. So if I want to know where that point is, all I need to do is plug in this x value, the x value of negative 1.5. If I plug that into the equation, it's going to tell me where the axis of symmetry is. And actually, I'm going to anticipate it's going to be somewhere up here, because remember, this is going to be an upside-down parabola because of the negative 2. So let's find out. Let's take that number, x equals negative 1.5, that's this point on the axis, and let's plug it into the equation and see what happens. I'm going to use a different color, just since there's so much going on here. And I'll write right down here. We'll do y equals, all right, so we will say negative 2 times negative 1.5 plus 4 times negative 1.5 minus 1. We're colliding over there. That's all right. We'll make it shorter in a second. So that would be when we have negative 2 times 2.5 times negative 2.5. Now we all know that I like fractions better, so I'm going to turn this into 2 times 5 halves times negative 5 halves, which will give us an answer of negative 2 times 5 is negative 10, times negative 5 is positive 50 over 4. And in case you're wondering what that is as an actual number, that would be 4 goes into 5 once with 1 left over. 2, it would be 12.5. Oh, that makes sense. Of course it is. So let's think about what I just did. I plugged in negative 1.5 because I know that's where the axis of symmetry has to be for this parabola. The reason I plug it in is whenever I plug in an x value, I get the output value, the y value that goes with it. So I plugged negative 1.5 in, and now I get a y value of 12.5. What that means is that that there is a point here. It just happens to be the vertex because I've chosen it that way. Negative 0.5, comma 12.5. That coordinate is on the graph, and I know that because I plugged in negative 0.5 as the input, and I got 12.5 as the output. So let's go here to negative 1.5 and then count up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 actually, and then a half is just above where the graph ends, which gives us 4 points to draw our parabola. Actually, if you want to, you can even make the mirror image of this point here. Remember that a parabola always has a mirror image. Yeah. Making sure I'm putting in the right spot. So since I know this one, if I want to mirror it over there, I can just, without having to do any extra work, I can draw it. I can connect these dots. It's kind of hard to draw a parabola here. It's a little wobbly. Oh my goodness. All right, that's just not okay. We need to try that again. Go up to the vertex and then down to the other 0. And there we have it, an upside-down parabola that I was able to graph using the information straight out of the factored form. Now, none of that information would have been easily accessible to us with the regular standard form if you go back and look at y equals negative 2x squared minus 6x plus 8. Those numbers don't mean anything special to us. But factored form provides, first of all, the zeros, the x-intercepts, very easily, because we just figure out what numbers would make the whole equation 0. We also can easily find the y-intercept because we just plug 0 into the equation and find out what comes out. And then it takes a little bit more work to talk about the axis of symmetry, but not that much extra work, because we know that it occurs right in the middle of the zeros, and we know that we can find any point on this parabola easily by just inputting the x value and getting the y value out. That's how we make coordinates like this. We can get an xy pair. All we need to do is plug the x in and we get the y out. So that is my second example. Now we're going to talk about this more in class. I feel like this information might feel a little bit much, but don't worry. This is just, again, me laying the groundwork. I'm trying to give you the big picture, and we'll take the time that you need to go over the examples in class so that you feel comfortable with it. Okay, that is that, and I will see you in class.